going to talk about model evaluation and selection, and also we're going to look at ensemble methods and imbalanced class problems. So model evaluation. So we know that depending on your split of training and test, you often get different results, right? How do we know which performance score actually represent the true performance of the model that we trained? We know that we need to use validation set and the final test set so that they are disjoint, that we don't bias our result. However, we still need method to actually estimate systems performance. There are some popular methods we're going to cover today. One is handout, holdout, use random sampling, and another is cross-validation. We mentioned this a couple of times. Probably some of you are already familiar with, and also Bootstrap. To compare classifiers, if we have trained models on which one works better than other, we can do statistical test. One most popular one is Ttest or paired Ttest to compare two models. We will also look at the ROC curves that can visually illustrate two classifiers performance on a two-dimensional space. Now looking at our confusion matrix. A confusion matrix has it's a little table structure as shown here. The vertical here we represent the truth, the actual class, and in the columns we represent predicted class. And based on the overlap between these two, we will have true positive cases, false negative cases, false positive cases, and true negative cases. If we, again, using our buying computer or not example, we have in this learning algorithm predicted this many buyers and this many people not buying, but our choose says you have a total number of 7,000 going to buy and 3,000 not going to buy. Our prediction is 7,366 buy and 2,634 not buy. Okay, so with this confusion matrix, we can define a large set of evaluation score. So first of all, we mentioned this before, I think, accuracy. Accuracy is all the true predictions, the sum of the true predictions divided by all counts, all total number observation. And the error rate is simply 1 minus accuracy. So all the false predictions divided by total number of observation. And on that, we could also define true positive rate, which is among all the positive cases, how many were predicted correctly by the system. This is also called sensitivity. People work in medical domain probably are very familiar with this sensitivity measure. In information retrieval, we call this measure recall. So this one thing has 3 names. It's sensitivity, it's recall, and it's true positive rate. False negative rate is defined as among the true positive samples, how many being predicted wrong. Accordingly, we can define false positive rate and true negative rate. So when we have false positive rate, we're looking at truly negative, the things that are negative being predicted wrong. True negative rate is among those negative samples, how many being correctly predicted. And true negative rate is also specificity. Specificity and sensitivity is a pair of measures that's used together to tell us how efficient a test, a medical test, for example, is, how how well the test can find true patients. Questions?
So in this case, can we say that the true positive plus false negative is always equal to 1? Like, and so the other two as well?
Right, yes. The sum of this is 1, and sum of this is 1. Correct. Two other measures we're going to introduce, position and recall. Again, recall sensitivity. So in case of information retrieval and many classification prediction problems, our goal is to predict, if we predicted true class if we predicted a positive class, we want this prediction to be correct. That is measured by position. Among everything that's been predicted positive, how many are actually positive? We also care about completeness, recall. Among all those positive examples out there, how many we have found? So this is all real positive things, and how many has been truthfully identified by us. So if you look at the position recall formulas, you will see the enumerators is the same. The denominators are different. This is all positive. Among all the positives, there are how many being found. Position is everything that we predicted, the machine predicted as positive, how many were truly positive. So perfect score for all those is 1, and there is an inverse relationship between recall and position. When you have higher recall, you often have lower position. And it's because when we have position recall 2 measurements to measure one system, sometimes it's hard to compare whether one system is better than another. Therefore, we use this F measure, which is a harmonic mean of position and recall. The reason we have to take harmonic mean, not the regular mean, is because, as we mentioned, denominators are different. Therefore, we cannot just sum them up and divide it by 2. We have to make an inverse and make sure that we have the same denominator, and then take the average. This gave us F score. This is the simplest form of F score. We call it F1. F1 implies there's the beta parameter being set to 1. 1 means that we care about position recall equally. If you care position recall differently, then you want to adjust this beta. It could be greater than 1 or less than 1, depending on your need. And the complete formula for F beta score is presented here. In practice, the most commonly used score is F1 score. Questions? Okay, then we're going to look at example. I picked this example on purpose. I deliberately may pick a case where the class distribution are not really balanced. We can see many people don't have cancer, very few have. If we use accuracy measure, we can see the system performs very, very well, almost 100%. But that's really not true, right? Because among all 300 cancer patients we only found 90. So our precision measure, I'm going to give you a few minutes to let you look at this and make sure that I did my math right. And also for you to appreciate the difference between accuracy measure and the position recall being a pair, and the sensitivity and the specificity being a pair to evaluate the performance. Did I do anything wrong here? Hopefully not. So one thing that we want to note is when you have a class, some counts, certain instances carrying one class label is much more smaller than the instances that carries another class label. Then accuracy is definitely not the measurement that you want to use to report your findings. It's still saying in current literature that those imbalanced classes performance being reported in accuracy. It's very misleading. Never do that. Okay, we can move on, guys. So so we know how to we know to use position recall and other measurements to score system performance. But since we cannot trust our scores in one run. We did one run and we found 90% of performance, and we trust that 90% is a truthful reflection of the system performance. No, we cannot. Therefore, we want to do multiple experiments using different splits of training and test examples to obtain multiple scores. When we have many scores, it's just like we sampling population and find their height and predict high school student height. We cannot really just pick one student and say all the high school student in the United States is 1.9 meters tall, right? So that's why we need to actually do multiple tests. Now, multiple tests, what are the popular methods that we can do all those splits to get the performance estimate? This is a reminder that we have training example being divided into training and validation, and we reserve the test data for the final evaluation. We talked about this at the very beginning. So now what we're doing now, all the schemes that we talked here are unlabeled data doing training and validation. Okay, so those two parts. The test data is reserved. After you're done here and you're happy with the performance, you move on to your test. Okay, so holdout method for very large data set. Our goal of doing repeated tests is to avoid bias in our estimate of the system performance. But for very large data set, the chance for you to be biased probably is not that great. So it's okay when you have large set data, you split once. You take 2/3 of the data, for example, it could be 3/4 as well for model construction and using the rest of the for model validation. Another variation of this hold-down method is to use random sampling, and then that will allow you to repeat holdout k times, and then your performance accuracy here means performance, not the accuracy error measurements. The performance is going to be the average of the performance and that you obtained through k rounds of evaluation.
I have a question there. For the holdout method, it's now training set and validation set, but where is the test set?
Oh, as I said, the test set is reserved for the final thing.
But how big should it be?
Test set?
Yes.
Well, we normally use probably because the labeled data is very scarce and very like valuable that we don't have lots of labeled data. In that case, the test data is about the size of the validation data.
Okay, thank you.
Yeah, sure. Okay, cross-validation. Cross-validation is one very popular method. It's used for medium here means fairly large, not super large. K typically takes 3, 5, 10, with 10 being the most common. When your data set is at the lower end of median sized, like you have maybe less than 1,000 or around that boundary, you might want to take 5. If you have thousands, then k equals 10 is the most typical setting. What we do here is we will partition our labeled data. So labeled data here, the training set part. We will divide that into k mutually exclusive subsets. And each set is equally, approximately equal size. And then we will take k minus 1 sets as the training example and reserve the last set as the validation. So we can, for k equals 10, we can actually do 10 tests. And then we get the results and we can average the results from the 10 rounds. We certainly can calculate standard deviation. A variation of cross-validation within dataset is actually small. This scheme is also used for dataset that's very small. Is you actually, every time you leave only one out. So every time you say you have 100 training examples, you use 99 to train the model, and test the model on the last one observation. And also you could do stratified cross-validation where you're sampling as stratified so that the class distribution in each fold is approximately the same as in the initial data. Where you have multi-class classifications or unbalanced binary class classification methods, this will ensure that the minority class got sampled into your training example. Questions?
Is the holdout this synonym for a test set, or is the holdout a validation set?
So holdout here is so holdout method is referring to this method, this partitioning method into two independent sets and run the example, then run the training and test. People would commonly call this validation set holdout, but this is different from the final test that you hold out. Does that make sense?
So it's mostly about the method. So even though in cross-validation you're sort of holding out some data.
We rarely call them holdout in cross-validation. We'll see this tenfold cross-validation. We will rarely refer to validation set in holdout, in tenfold cross-validation set as holdout set. It's more often saying when you use the holdout method. So the difference here is actually the partition here is mutually exclusive. Cross-validation, every time the data sets that you used, one run and the next run have completely have different test and training set. And holdout, you just need to partition this into two independent sets. When you repeat them, there could be overlap.
So so I see. So if I understand correctly, then in the large data set, you may still repeat, but you just arbitrarily split 2/3,
Right.
1/3. But in cross-validation, you start off, let's say if you're doing tenfold, you make 10 mutually exclusive subset, and then you just cycle through the 10
right.
to pick which one is validation.
Exactly.
Thank you.
Yes. The third method, Bootstrap, used most often on smaller data set. The results from Bootstrap tends to be optimistic, so the estimated performance is better than the true performance. But for small data set, this is one possible way of doing it. The idea is to repeatedly sampling with replacement so that you can generate hundreds of runs. Here, the most common one is called 0.62 Bootstrap. This name comes from the fact that we do sampling with replacement. So we have a data set with D tuples, and we sample it to D times with replacement. And our result training set, again, is D samples. As you can see, some samples in this set is redundant. It's the same tuple being sampled multiple times. And this set is going to be used as training set. The rest of the data will be the test validation set. So if we look at the probability distribution, no matter how many times you sample it, you're going to have around a third of data for the validation and 2/3 for the training. And you repeat this many times. The time used, from 30 to hundreds rounds. Then your overall accuracy measure or the performance measure is a weighted average of your training and a tested data set. Questions? Okay.
So is the formula just saying that the reason it is the weighted average is because you're replacing, so there's not two independent sets for test and training?
That's a reasonable observation, but I think this probably also has something to do with want to really make use of all the data set, the data points. And also, I believe there are statistical theories behind this, which I'm not familiar with. That make it tends to be reflect the true performance. However, empirical studies have shown that this measure tend to be optimistic. I know I didn't answer your question perfectly.
Thank you. I was just wondering because,
yes.
Normally the accuracy will only be on training set. On testing set, not on training set, but this formula is including that in the formula. Right. So that's kind of where I was a little bit wondering.
My intuition is because we always reserve just 1/3 for test. When you have very small data set, the test, the score cannot be really trusted either. So to use all the data set labeled set that you have there, they assign a lower weight to the training set performance. Yeah, that's a good question. I can research this more.
Thank you.
So which one is better, right? So we look at 3 different schemes that allow us to repeat repeatedly test our models. Then we can actually, it doesn't have to be tenfold cross-validation, but you certainly have many runs that you can obtain the mean error. By error and the accuracy here, I all refer to the performance. You can decide what performance scores that you want to use. I think this is all, we all know that, right? Test the statistical significance between 2 means and obtain confidence level for the test. T-test, in the assignment, I deliberately added the paired T-test. When you have exactly the same training and validation set used for different rounds between 2 systems, you will use paired T-test. Otherwise, you use unpaired T-test. There's methods in R, in statistical packages could help you to run T-test. Another way to compare models is to use ROC curve. Receiver relative, some places call receiver operating characteristics, others relative operating characteristics. It doesn't really matter, it's ROC curve. The idea is to allow you to see the trade-off between 2 measures. The most typical used one is the true positive rate versus false positive rate. This is the 1 minus specificity, 1 minus specificity. So this is typically popularly used in medical diagnosis. There are variations. Similar ideas can be carried to precision recall. You can have precision recall curves. I mentioned it somewhere. There is a link that you can check it out. So the idea is we will plot two different systems or multiple systems performance on this two-dimensional space. The scale is from 1 to 0 and 1 to 0. Okay. And this line represents random performance. So system knows nothing, random guessing. The performance is going to lie on this line. And those lines above this random line depicts the performance of different systems. We want the system to cover this upper area as much as possible. More area covered under this curve, the better the system performs. Because it's closer, the true positive rate is close to 100%. Let's see if I have mentioned everything. I think so. We'll run examples so it becomes clear. To use ROC curve, the model prediction must be represented using probability. Many methods give probability scoring. Last time when we look at the have we looked at the probability? I think so. In decision trees, and today we're going to also look at probability in support vector machines. The system can predict a class. It can also predict what the probability, I think this instance belongs to this class. So to use ROC curve, the model must return probability of predicted class for each observation. In this little example, we have 10 observations. We have their class labels. So this is the truth. This is the gold standard, ground truth. And this is our system's prediction. Our system predicted with 90% of probability, the system think that's this class may be a positive class. So this is what we have to start with. Then we will sort those probabilities from the greatest to the smallest. The idea is we're going to apply different probability as our threshold to generate our prediction. And then we're going to compare our prediction with the label. That would allow us to compute true positive, false positive, true negative, false negative. And that will allow us to compute a true positive rate and a false positive rate at different threshold.
Question here. I think what it's, if I understood correctly, I'm just trying to confirm, is the probability column is saying, like the first row with 90% probability, this probability is always to classify as positive, not
yes.
One class or the other. It's just always one class.
Exactly. This is designed for binary classifiers. It's a two-class problem. So we can go through this. I think one of the homework assignment asks you to do a graph. So system, we sorted this in order, right? First, we take 0.9 as our threshold. Anything has probability of 0.9 or above going to be categorized or classified as positive. So this class, the first observation going to be classified as positive by us. All the rest are going to be negative. This is how we apply this threshold. At 0.9 threshold, the first instance is going to be predicted as positive. All the rest are negative. So based on that finding, we can see our true positive is 1. We predicted 1 positive, and that one is true. We only predicted 1, and so there's no false positive. we predicted lots of true negative because this is negative, this is negative, this is negative, this is negative, 5 true negative. But we also predict lots of false negative. All those should be positive, but we predicted as negative,
I have
right?
a question.
Yes.
So for the first row, true, it's a true positive, right? So TP is 1 here.
Yes.
Why TN is 5? True negative is 5.
Yeah, because we predicted all the rest to be negative, right? And they are negative cases. So our prediction matched the truth on those 5 negative cases.
Oh, okay. That the third column
Yes.
is threshold for switching between positive and negative.
It's true negative.
I know. The third column, like probability column,
Oh, here, yeah.
the threshold that is used to switch between positive and negative cases.
So yeah, like Bart is he just got clarified that this is a binary classification problem. Anything, if we predicted a probability greater or equal to 0.9, we're going to label that class as positive. All the rest going to be negative.
So these are the thresholds that we choose, 0.9, 0.8.
No, this is the system's output. So
Oh, okay, I see. This is the system's output for
right.
For tuple 1. Okay.
Right. So for example, this case, the system predicts the probability of 0.54 being positive.
Okay, I understand. Yeah. Okay.
Really understand. I just want to make sure all the other students also get it. Okay. So now we move down our threshold. We come down to 0.8.
Professor, we're having trouble hearing you.
Shall I repeat? I'm in my office. This is the best network place that I could find.
It was good. Suddenly the quality dropped. I don't know why.
We will try to manage. If you don't hear me, I will repeat.
It's fine now.
It sounds good now, yes.
Yeah. So now we move down to 0.8. Here, if we use this as threshold, then the first 2 instances going to be predicted positive by our system, and all the rest are going to be negative. So in this case, we have 2 true positive. We predicted 2 positive, and both of them are true positive. We don't have any false positive because we didn't predict anything being. We only predicted 2 positive, and they are all correct. And now we still have 2 negative because we predict, starting from row 3 down, we predicted them to be all negative. Among those, 5 were negative. So we have true negative of 5, and then false negative 3. Because this one is false negative, this one is false negative, this one is false negative. We predict them as negative, they turn out to be positive, right? So we do this, going down this list, we fill out this PT, FT, TN, FN. That allow us to compute true positive rate, which is here, and false positive rate, which is here. We will have those values filled up, and then we will plot this on this graph. So the first point is right here, 0.20, 0.40, and then 0.40.2 is here. We plot those dots, we connect them. When we have lots of data, we don't have a smooth line, but smooth curve. But in this case, our graph is rather edgy, but this is our ROC curve. The area under this curve shows the performance of the system. Questions? Okay, looks like we can all do that. Great, excellent. I'm mentioning position recall curve. When you have imbalanced classification problem, not medical diagnosis or test, medical test whether you have this virus or not. For position recall curve, because we wanted to make sure that the all the positive classes there are has been recovered by us. So we're going to plot the position recall curve going to look like this, not that. If you're looking at my cursor, this ROC curve going to like this, but position recall curve going to look more like that. It's again, the area under the curve shows the performance. But when you have imbalanced class problem, position recall curves definitely show the performance difference. I have a link here for you to check out if you wanted to. There are also other multiple class classification performance can be plotted. If you convert your multi-class classification problem to multiple binary class classification problems, you can continue use ROC curve, or you can do the averaged performance and using ROC curve or position recall curve. Okay. Okay. So we just talked about two ways to compare system performance. One is using statistical test. Another is to use graph to visually show the performance difference. Issues affecting model selection. So we have measured them, and now we have different results, and we compare different results. How we're going to select the models. Effectiveness, which means the classifier's performance or regression performance, is how good, how accurate the labels has been predicted. But effectiveness may not be the only concern, only criteria. We also care about speed, how much time to construct the model, how much time it's going to take to use the model. Typically, classification prediction time are very quick, small. That's a little consideration. The construction model is a major consideration. For example, if you train a neural network, it could take days. Adjusting anything that's going to take another several days. It will certainly affect your model selection decisions. Robustness is actually also very, very important. A lot of times, because machine learning has typically have the tendency of overfitting, robustness is very critically important. I think we mentioned once, if the smaller models, simpler models are often preferred than complex model, even if the complex model give you maybe 2% to 3% more of performance advantage, we would still prefer the simpler and more robust model. Scalability, how fast, how does the system scale with larger amount of the data? Interpretability, understand the insight provided by the model in the relation of the data ethics. When we use big data to predict something that's actually going to affect a human being's life, then interpretability becomes a major issue. Why do you classify me as a risk person that deny my loan request? I want an answer. You cannot just say my AI system tell me to deny you. That would be too crude. So interpretability is a very important measure.
I have a question here. Is robustness and effectiveness for the noise missing values, would that not show up when you're doing your testing? So it may affect your precision or your
That's a good catch. I need to update the slides. Robustness at a higher level. So handling noise and missing values, I agree with you. It belongs to effectiveness. Robustness to me means that if you trained your system here, and you apply your system to another data set, does the performance holds? So that when you have, because training example is always limited. When we deploy this model, train the model somewhere else, the new unseen example is unpredictable. Any data could come in as long as the data falling into this domain, and the system could actually perform very bad. You could say this incoming new data has lots of noise that the system does not know how to handle. For that, in that sense, you can say handling noise is also part of the robustness. But I think you get my idea. I think we're on the same page.
Yeah,
Robustness is how system performs in a slightly different environment.
so is it like a form of generalizability, maybe?
Yes. People also call it portability.